Good evening, Jaffer sir. Am I audible?
Good evening, sir.
Good evening, Dr. Goyal.
So, how are you, sir?
Is my voice audible?
Yes, sir. It is clearly audible. If possible, can you please turn on your camera?
Of course, sure. So we'll test that also. Is it visible now?
Not yet.
Not visible?
No, it is showing Z only. Just the icon with capital Z.
Well, I have turned on the camera, so I'm not sure what is happening.
It's okay, sir. So, first up, very good evening, and we are very grateful to you that you spared time and you are here with us today.
Thanks a lot. Thanks a lot. Before starting, can we also test whether you are able to see the slides?
Yes, sir, sure. We can do the testing.
Is it visible?
Yes, sir. Your slide number 24, now 22, on 57, now 21, 19, and 4.
Great. Thanks a lot.
So, shall we start, or you would like to have a short conversation with the participants as they are increasing in number? Right now, we have only 36 participants. Maybe they are joining.
Sure. So you are able to see the slides, right?
Right, sir. Coding and decoding for 6
Yes, but it's not showing that for me. Let me see how the background comes out. I'm not sure able to see what you are seeing.
Okay.
Is the camera coming? So it's still not coming.
Actually, your camera is on, but camera feed is not live. It is showing the icon with a capital Z. That's
So
it.
how do I make it live?
It is showing. Dr. Verma, how can we help him? Because he is saying he has turned on the camera, but it is not showing the live feed.
Sir, on the right hand side top, there is an option camera and there is a drop down.
Yes.
Please click on that and then you can select this none option.
Huh?
Oh.
There is a camera integration option appear under that part.
Yes.
So it is appearing or not?
It is there.
So there is a background. So please check none option.
Background would come on in the viewing thing. It is showing the background there.
That the shutter of your camera is on or not? Check the shutter of your camera in your laptop or the
It's
device.
on. I can see myself in my camera, so I have put
Oh,
on my camera also. Maybe I
okay.
should disable that. Let me do
Be-
that.
yes, because now the icon is not there. Some feed is there, but it is blank. Now the icon is back.
Uh-huh.
Yes, sir. Your live feed was there just for a few seconds.
How about now?
Now
Yes,
it is
sir.
available, sir. Yes, yes.
Yes, sir.
Yeah, thanks a lot for helping. So the slides are also available.
Yes, sir.
Yes, sir.
Okay, so Soumya ma'am, please.
Yes, sir. So, sir, if you allow, can I read a short bio of yours in front of the participants?
Go
A
ahead,
short
madam.
introduction.
Please go ahead.
Thank you, sir. Thank you. So, dear participants, on the day 4 of this FDP and session 7, we do have Professor Dr. Zafar Ali Khan Mohammed from IIT Hyderabad today with us. He has received the BE degree in Electronics and Communications from Osmania University, Hyderabad, India in 1996, MTech degree in Electrical Engineering from IIT Delhi in 1998, and the PhD degree in Electrical Communication from IISc Bangalore in 2003. In 1999, he was a design engineer with Suskin, Bangalore. From 2003 to 2005, he was a senior design engineer with Silica Semiconductors, Bangalore. In 2005, he was a senior member of technical staff with HelloSoft Hyderabad, and now he is currently a professor with IIT Hyderabad. He has more than 25 years of experience in teaching and research, and he has been a chief investigator for a number of sponsored and consultancy projects. He has made noteworthy contributions to space-time codes, and space-time block codes designed by him have been adopted by the WiMAX standard. His current research interests include signal processing for wireless communication, MIMO, cyber physical systems, cognitive radio, and radar. Dr. Khan was a recipient of INAE Young Engineer Award in 2006 and Vishweshwarya Young Faculty Research Fellowship since 2016. So, such a big profile. I am completely overwhelmed. So, let's welcome him. And, sir, over to you. I'm again very thankful to you that you are joining us, and we are so blessed that we will hear from you. So, sir, the audience is all yours. You can start the talk.
Good afternoon, good evening, everybody. So I hope you are fresh enough for some technical discussions on coding and decoding for 6G. Am I audible to everybody?
Yes, sir. You are clearly audible.
Yes, sir.
Good. So this work is basically, as you can see, coding and decoding for 6G is a journey of almost 10 years where we have been trying to come up with low complexity decoders. As we go on, we'll see that. And it is work of three of my PhD students, Praveen Sai, Aqib Patel, and Abdul Mateen. The idea is from Abdul Mateen. The initial theory work was from Aqib Patel, and Bere Praveen Sai made it what it is now. So with that, I'll go inside. We'll see. This is a brief outline, and you'll see that the idea is very simple. Okay, but the possible impact is quite significant. And this list of publications, we have some 8 publications going into this work, and some 3 patents coming out of this work. So from a background and context point of view, if you've been watching the evolution of 4G to 5G to 6G, the new cases that have come into picture in 5G was basically reliable communication, low latency, and energy efficiency. And this was especially because of three categories. That was enhanced mobile broadband, massive machine type communications. In fact, it was there in 4G also. But the difference from 4G to 5G is mobile broadband is become enhanced, machine type communications has become massive, and low latency communication has become ultra reliable low latency. Okay, so these were the additions in 5G, and the 5G standard was built around these new use cases. If you are following for 6G, this enhanced has now been, they call what is called as KPIs. So these are basically projected use cases for 6G. So the enhance has now been uh, replaced by what is called as extreme. Okay. So you have extreme machine type communications, you have extreme mobile broadband coverage, you have extreme ultra reliable low latency communication, so on. Okay, so the principal idea is these the underlying requirements are going to be much more enhanced in 6G. And the moment you go to IoT, URLLC, and MMTC, the underlying problems are similar but slightly diverse. For example, short block length is required for all three of them, and I will show you why. Okay. The reason is, if you make up the packet large, or you have a so that if you have a larger code, that would require a larger block length, and a larger block length inherently will actually put in constraints on delay, because you have to receive the entire code block length to decode it. Okay, so that's a problem. You cannot have large block lengths. Even though we have LDPC codes, turbo codes, okay, for these IoT, URLC, and MMTC type, and the 6G versions of these, that is called as extreme. Okay, so the requirement for short block length will remain. Okay, and the problem is, when you trade block length, you pay in performance. So this is not a trivial requirement that you have a short block length code. And if you have been following the standards, some of them would use repetition code, length 8 repetition code, to guarantee ultra reliable low latency communications. Okay, IoT uses CRC. IoT and MMTC both use CRC, with an option in 5G to actually use turbo codes or LDPC codes or even polar codes. Okay, but nobody actually uses that. And for reliable communications, the major shift from 4G to 5G was on required bit error rates. So URLC for 5G is 10 power minus 9, and for 6G it is around, the KPIs have put it at 10 power minus 12. So pico error rates. Okay. Uh, So you want very reliable communication. So one error in 10.9 bits on the average. So that's a very stringent requirement. And because of this, and I have already said while you were discussing short block length communication, that for IoT and URLC, because reliability is important, so they trade in rate. Repetition code of rate 8 means you are putting the rate down by 8. In contrast, for IoT, you are using CRC, so this is a very poor. In fact, CRC was not designed for error correction. It so happens, as you will see later on, that it does have some error correction capabilities. Requirement wise, 5G requires 1 millisecond, and the extreme URLC for 6G is now 1 microsecond. So this requirement has become much more stringent. And the underlying principle of all of this, why we don't actually put in turbo codes or LDPC codes, is these codes require both. The decoding is not simple to be useful for IoT. For example, you can put a turbo decoder or a iterative decoder, but that will actually suck the battery of an IoT device. So it is never preferable to have high complexity decoders. They wanted simple decoders, and that was one of the major reasons they have gone for CRC and your repetition codes. So what we are trying to do is, because the constraint is coming from the decoding side. Coding side, because you need a good decoder, all good codes. For example, you can have a BCH or Ritz-Horman code of dmin or minimum distance 8. That's possible, right? But you won't go in for it, because the decoding complexity is a power of the block length. So even if you have a block length of, say, 64, that is, or 128, that is typically used for CRC, it is not usable. You cannot have that much complexity for IoT. Okay, so the underlying reason for this work is to make decoding simple. So that's why the underlying theme right at the bottom of the slides, you can see next generation decoding solution. Yeah, many people, in fact, if you are following the coding and decoding, it is one of the themes of all communication these days, because people understand that it's one of the important areas to work these days. Okay, and most of them, they are actually applying AI to get efficient or better decoders, but AI requires a lot of training. So inherently what I felt was, or what our group felt was, that's not a approach we can take. So we'll try to do some brute force decoding from start, and if you see, the idea is very simple. And with that introduction, and I will stop and ask if you guys have any questions regarding this introduction.
Dear participants, if there are any queries, then sir is asking if you have any query, then let's make it interactive session, and it's an open session. We are so grateful to Professor Zafar that he's making it an interactive session. So if you have any query, please raise your hand so you can directly turn on your mic and you can raise your queries. I think, sir, we can go ahead. And if
Yes, so
there are
I
any
assume you are
queries,
all following what I am talking about, right?
yes, sir.
Good. So the problem statement is this, based on this discussion, that we want to have short length codes with good decoding. And if you ask me why you have put coding also, the reason is, if you give a simple decoding algorithm, you can use the best codes that are available. So what we are actually doing is, we are enabling use of high performance codes, BCH rich formal codes, which were not usable till now, except for cases where it was extremely necessary, as in space communications or rocket communications. So they were never used because of the complexity involved. So what our work will do is enable the use of these codes for, or rather open up the use of good or the best known codes for the standard. Okay, theme, that's one thing. The second thing is, for a fading environment, what is important is diversity, and diversity is the slope of the BER curve. Okay, the bit error rate curve that we, defines any code or any communication system. The slope of that defines what your diversity is. Okay, so that's what we'll try to preserve. So be with me. I'll skip this slide. So we have a binary code of length n. We have k message bits, Typically, linear code is generated by a generator matrix. You have a parity check matrix. Remember this, if you don't even have a very strong coding background, remember this from the code Hamming codes. I hope all of you are aware of Hamming codes.
Yes, sir.
Yes. Well, some noise at least from other side would be useful. Yes, of course, Dr. Goyal is there, but some noise at least from others would also help me, because what I give depends on what you ask also.
Yes, dear participants, we are so lucky that sir is asking to be interactive. We can raise our queries without any hesitations. Let's make it an interactive session and put your efforts, and you can clear your doubts also, even the basic one or the advanced one.
Well, you are all of you are aware of Hamming code, right?
Yes, sir.
Okay. So I'll assume that. So Hamming code has a distance of 3, and your generator matrix is of size 4 cross 7. So you take 4 input bits and output a code of length 7. That is n. Okay. And d mean is
प्रोफेसर सर आपका ऑडियो एंड वीडियो फीड has been stopped. Dear participants, don't be afraid. I think Professor Sir has some network issue or some technical glitch, so do not be worried. He'll be back within few seconds. Just stay tuned. He's coming back.
Am I back?
Yes, sir. Welcome back.
Thank you, but it's not my fault. Microsoft Teams has stopped saying that it is my app is 28 years old and it's asking me to
It's okay, sir. It's okay. It
update it.
happens.
So I
Sometimes it
have now
happens.
logged in back with this in the browser. I hope it works. But it is not giving me sharing
Sorry
option.
for inconvenience, sir. So we are
No,
really
not at
sorry.
all. It's not allowing me to share the screen now. Can you
Okay,
probably
okay.
from there?
Let me check. Let me check. I think now you can share. I have made you presenter, sir. Now you have the rights to share the screen. Please check.
Yes, I have it.
Yes, sir. We were here only. We were
Yeah,
talking about parity and the
yeah.
Hamming
Just
code.
give me a few minutes. I'm trying to make it full screen.
Yes, sir.
Yes. So for we are discussing the Hamming code in this context. So for a Hamming code, your generator matrix is 4 cross 7. You take 4 input bits, generate 7 code bits, and the parity check matrix gives you the syndrome which you actually use to identify where the error is. And the minimum distance, that is any two ports of this particular code, is at a has is different from any other code in 3 places at least, and that is why it is called as minimum distance of the code. Okay, so with this brief introduction, you don't send bits as it is, you need to modulate it, and for simplicity I'm assuming we are using BPSK. Okay, so you transmit a legitimate code word. It is mapped to a sequence of minus ones or ones because that's what your BPSK transmits. And what you receive is a noisy version of what is transmitted, that is SJ. AJ is the fading quotient. That's the reason of that is the major problem in wireless communication, and WJ is the noise. All codes still now have typically been designed for uh, additive noise and adapted to fading channels. Okay, you will see why I'm saying that later on. We also assume that channel state information, that is AJs, are known at the receiver. So this is what we are giving to the decoder, and so the received code word. And how do you get the received code word? From yj you actually demodulate to get the vector r. So you get a sequence of minus ones and ones, which are then converted back to ones and zeros. So it's a word, uh, uh, tuple, binary tuple of length n. Okay, a vector, binary vector of length n. We also give the reliability vector. You can assume they are the channel coefficients. What you get is a proper code word. Okay, the if you remember from the Venn diagram decoding of Hamming codes, you get there are many possible receive vectors. There and the possible number of vectors are 2 power 7. Possible code words are 2 power 4. So you have to map those 2 power 7 code words, received words to 2 power 4 code words. Okay. And once you are able to do that, you get a decoding message. So that's the visual representation of what we are doing. I'll skip this. And this is what is called as diversity order. It is the slope of the BR curve. Okay. Minus power D. When you do hard decision decoding, that is your Venn diagram decoding or your syndrome decoding, which are the two popular uses of Hamming codes, okay, what you lose is the diversity. This power is basically now d min minus 1 by 2. So if you substitute d min is 3 for Hamming code, this would be only 2. Okay, that is, it can correct one error, so it can give you a diversity order of 2. That means your BER curve has a slope of 2. So when you have a slope of 2, what it means is as compared to 1, if D is 1, your slope is slower, so you have to increase more SNR to actually get the same curve. If it is 2, it is better. If it is 3, is much more better. In fact, that's where most of the standards work at. D is 4. Soft decision decoding, that is, you use the vector y itself to directly map to the code word. This preserves diversity. So the slope here for Hamming code would be 3 because d min is 3. So that is a major drawback in using hard decision decoding. So the coding decoding that we knew till now doesn't work because of these two results. Hard decision decoding loses diversity, soft decision preserves it, but its complexity is exponential in the block length n. So for 7 for Hamming code, it would be actually a power of 7. Okay, and higher order codes, it would be basically difficult to actually do any of it. So what we have come up with an approach, and our competitor in this new approach is MIT, and they have come up with what is called as GRAND, guessing at random additive noise decoder. Okay, so they have been working almost simultaneously with us. Then they have proposed a new group of decoders, and very similar to our work but different. We have a different set of decoders, and if you are aware of coding theory, all the Venn diagram decoders, syndrome decoders, any decoders known till now actually fall in guessing code word. So what you do is you receive the vector and you try to guess what the code word was. In contrast, these two approaches, our approach and the MIT approach, is we said we rather than guessing code word, it is much more simpler and less complex to actually guess the noise in many cases. So the pink ones are what is our contribution. Any questions in that? No questions. Are you
No
there?
questions. Yes, sir. We are here. You please continue. If I have announced among the participants that if there is any query, they can raise their hand, and if anybody raise the hand, we will ask them for the query. And another provision we have made for the question answer round, sir, they can drop their queries in the chat box, so we
Okay.
can address the questions, all the questions all together at the end of the session.
Fine. Thanks a
So
lot. So I hope you are following that, because this work builds upon what I am saying till now. So rather than keeping you in suspense, we'll bring in the idea. So I'll skip this. So what you have is the reliable received code word R1 to R7. I'm doing for Hamming code. So you have 7 received bits that are represented by R1 to R7 in red and pink. This one. Okay. Above that, you have a reliability vector. The channel coefficients H1, H2, H3, H4 till H7. Now, can I use a pen here? Let me check. No. So I'm just giving you a few values. Say I know H1, H2, H3, and then say I'm using a, rather as of now not using Hamming codes, I'm using a parity check code. So you are aware of a parity check code?
yes, sir.
Yes. So what do? You add one extra parity bit. You have n-1 data bits. You add
Data
one
bits,
additional parity bit,
parity
right?
bit.
So and that's a simple code. It tells you how much, whether there is an error or not. It will detect one error.
Right.
It will not detect 2 errors. If you have 2 errors, it will say the code word is good, right? But given with that information, what I'm saying is R is your received code word. I have done a parity check on that, and I know now that there is an error. That is, parity doesn't match. Additionally, I have this vector. The first one, it says what is the channel coefficient. For example, let me put H1 as 0.1, H2 as 0.2, H3 as 0.3, and H till H7 I'm just adding 0.1 and 0.1. Now tell me which bit would you expect would have least, which is most likely to be in error?
0.1?
Let me put it much more simpler. Let H1 be 0.1 and rest
0.1.
of them are 1.
Hmm.
I'm saying there is an error because parity is not matching. So
Right.
which one, which bit would you expect to be in error?
H1?
Of course, because
Odd parity? The concept of odd parity, I guess.
yes, you use odd. Yes, let us use odd parity because we have odd bits.
Hmm.
Okay, so I know there is one error, and from the channel coefficients, I know that H1 has very poor SNR, so it is most likely to be in error. So what we have proposed and what Abdul Mateen idea was, let us flip that one bit R1 and check.
Oh.
Okay, it's a very simple decoder. Just flip the bit corresponding to the reliability vector here, and that works wonderful. Now for Hamming codes, you can detect how many errors? Correct, one errors. You can detect
Hmm.
3 errors, and
Hmm.
that's there in all digital communication books. So I assume you understand that.
Yes, sir.
Okay, so coming from parity check codes to Hamming codes, here what we are doing is, because we have, there's a possibility that 3 bits are in error, and your Hamming code will tell you that it is not is error. So based on the same concept, suppose I am saying H1 is 0.1, H3 is 0.2, H6 is. So in this example, what I am saying is H5 and H7 has the smallest value. So rather than going and flipping all the bits, what we are saying is if you flip 1 bit, 2 bit, and then the combination of these bits. So how many possible combinations are there? I am flipping 2 bits in all possible combinations. So it will be 2 power 2. So 4. Okay. In general, a Hamming code will detect 3 possible errors. So using the syndrome will detect which bits are, whether the syndrome is matching or not. And based on that, we'll flip a combination of 3 bits. That's 2 power 8. So I'll do just 8 tries and then say I'll definitely get a code word, and I'll decide that is the code. Got my point?
Yes, sir. It's clear that for the syndrome, as per the equation, it is R dot and H raised to power T, so it can be solved.
There's another example here. You see, you have the set of vectors H here, the received bit here. And what we want to now do is flip number of bits corresponding to the least reliability vectors. So the least ones are now marked in green. And from here, we mark them as vectors to be flipped and use all possible combination. One combination is put in here, so it doesn't work. It doesn't satisfy the syndrome. I change it again, and this one actually satisfies the syndrome. So the syndrome now says it's not in error. Okay, so this algorithm we have called as flip decoding for Hamming codes. Theory wise, you can prove that this achieve diversity. Curves wise, then that's what I think most of you will appreciate. This, the red curve is your Venn diagram or syndrome decoding of Hamming codes. This is a soft decision decoding of Hamming codes. Its complexity is 2 power 7. You have to 2 power 4. You have to check for all possible code words. Okay, and this is only 8 tries, and your what you see, there is a significant improvement. Most importantly, the curve, BR of the curve is now changing slope faster. So what you see is for higher SNRs, a smaller increase in SNR will give you much more advantage, and that is going to be useful for 6G because we are looking at a diversity of 10 power minus 12. So actually, I should have extended these plots to 10 power minus 12, but that's fine. It does give the impression. This is for a 7-4 Hamming code, yeah, and similar results for 1511 Hamming. right? So you see the slope changing faster, and by the time it actually goes to 10 power minus 12, you can hardly see a advantage of almost 10 dB. Yes, and there is a degradation compared to soft decision decoding because that's an ML decoder and that's supposed to be best. But the complexity is significantly smaller compared to power 4 with 8. So it's an order of one order better, right? And for this 10, 3126 Hamming code, our complexity still remains 8 only because it remains on D mean. It doesn't depend on N. While uh, soft decision decoder would actually use 2 power 31. So it's already very difficult to do the soft decision decoding. So most practical cases, so your soft decision decoding is impractical, right? So based on this success, what we said was we let us go and apply our decoding approach to CRC codes. So CRC codes, they are uh, uh, the codes of choice for IoT. They are the, and one of the examples is we have put in here from a .15.4. It's a 16 length polynomial used because CRC codes can be easily implemented using cyclic shifts, right? Cyclic shift registers are used for implementing these CRC codes. They have a dmin of 4. So from coding theory wise, you can actually correct how many dmin minus 1 floor plus 1 dmin minus 1 by 2 floor errors. So that would be 2 errors. But unfortunately, there is no decoder known for CRC codes. While all of you must be aware of CRC codes, you just whatever you receive, you divide by the polynomial. If it is non-zero, you say there is an error. Otherwise, you say there is no error, and you pass on the code. Okay, that's a typical use of CRC. And if you are following the latest research in this area, people have come up with decoders, not very so simple with CRC. They are not in the textbooks. Still, they are in some research papers recently, last 2-3 years, where they show how you can actually do some decoding. One possible approach is that table decoder that you all of you should be aware from Hamming codes. You make a similar table for CRC codes and do it. Again, it is quite complex, and unfortunately, it doesn't save diversity. So diversity order, it takes a hit here. So the performance, even though it is better than just the CRC, it is not as good as what should have been for d mean equal to 4. Okay, and the main reason is CRC is was designed for not for correcting errors. It is designed for detecting
Detecting
errors.
errors.
You're right.
Yes,
So
sir.
that's the approach. Now, what we do is based on the approach we have done. So d mean is 4. We'll select 3 bits. Okay, d mean minus 1. We'll flip them in all possible combinations. Okay, and then show that the diverse. You can actually show that this achieves diversity order of 4. I'll not show if somebody is interested. Even it's already published, so you can also see that online.
Yes,
Okay,
sir.
see the curves here. Okay, so your simple CRC code, which was still now used just for detection, and IoT applications, the reason they don't use any other codes and they just want CRCs, they are saying power is very important for us, so we won't put a compute power, any heavy compute power in CRC codes. No, but the simple decoder where we are flipping 8 possible combinations, you see the advantage here. For the same SNR of 30, where while your detection is somewhere at 10 power minus 3, right?
Yes, sir.
For 10 power minus 3. And for this flip decoder that we are proposing, it is around 2 into 10 power minus 7. So the gain you see here is almost 10 dB. One simple decoder you have put into the CRC, and your IoT device is suddenly start working fabulously. Okay, so because dmin is 4, CRC should actually have been better than Hamming codes, right? but which is never designed, so there was no decoder available till now. So you can start understanding the implications and importance of this work. This is for another code length. Your soft decision is not possible at this code word length, see 80. So 2 per 80 combination not possible, or even 2 per 64 not possible. Here it is 2 per 168, not possible, right? But for our case, it's fixed complexity. It depends on d min. D min is 4 to 2 power d min minus 1 combination. So that is 8 combinations, and you have a decoder which corrects 3 errors. Not all possible 3 errors. And that is the difference from traditional decoding and the decoding. Traditional decoders, you would correct all possible errors. Our decoder, we don't correct all possible errors. We can correct enough number of errors that the diversity order is preserved. That's the main difference in the approach till now. And that's also the difference between grant that came from MIT and our work. We have prioritized working for wireless channels, while grant still comes from the old school, that is, you are actually trying to correct all possible errors. Okay. Soft decision decoding doesn't correct all possible errors, but that part was hidden till now. Our work has brought that out. It shows actually that in soft decision, you're not just correcting for a Hamming code all possible when errors, you are actually correcting some 2 errors, some 3 errors. Our code, what we are doing is we are not also correcting all possible 1 errors. We are correcting some 1 errors, some 2 errors, okay, and enough of these so that we preserve the diversity. The results are here for you to see. Okay, so we have now weaponized this CRC. It is no longer a docile code that detects error. It can now work very well. So any questions till now? No.
It's going really well, sir. We can continue.
Yeah. Going back, if you have been following, there is a slight performance gap. From a coding theory perspective, if people would like to compare with the best, and there is a gap. There is a 3 dB gap here for Hamming cores. Okay, there's a 2 dB gap for PCC cores, and there's a 4 dB gap for CRC cores for lengths that are possible to decode. And these lengths that are used in the standard, that are suggested by in the standard 80 cross 64 or 184 cross 168, those are not decodable by soft decision. So actually there is no comparison in this case. Okay, higher lengths much more difficult. So based on this approach, we said we'll now diversify and come up with a decoder that works for all decoders. Okay, so you can start thinking. The idea is very simple. So for Hamming codes, we flipped d min was 3, so we flipped d min minus 1 possible bits. That was 2 power 2, that is 4 combination. For CRC, d min was 4, we flipped 2 power d min minus 1, that is 2 power 3, that is 8 possible combinations, right? So, and among that, one of them would be the received code word 00 itself, and that's why you have this second minus 1 coming into it. So the complexity actually is now independent of n, and it now depends on d min. You can say d min depends on n and k, but the point is it depends on n and k. So it's possible to design large codes, small d min. An example is your CRC code or Hamming code. So general approach, again, what you get is a similarity index. Okay, you get the received code word, you have the reliability index. First you sort the reliability in the ascending order. You get the permutation function for that sorting. Apply the same sorting to the received signal. Okay, and then based on d, that is d min minus 1, you segregate the received word into 2 parts. The lower part is the LRB, okay, least reliable bits, and the upper part is the most reliable bits. So d min minus 1 lower bits we are segregating as least reliable, and the remaining n minus d min minus 1 bits, we are saying they are more reliable or most reliable. Okay, that's the segregation. Right? And then we'll add a error vector. This 100 is basically an error vector. We don't add any combination in the most reliable bits. We check for all possible combination in the least reliable area. Okay, so for this error combination 1000, you flip only one bit. Okay, and that's why I am saying this decoder is noise type. We are guessing the noise. You are not guessing the code word. You got the point now? Yes.
Yes,
Okay.
sir. Yes.
So once you flip that bit and then you apply the inverse permutation, and that's what is your code word. And then you check with the syndrome. And if the syndrome is non-zero, you say a code word has been detected. Otherwise, you repeat the process. That is, you go and change the noise vector. Okay. So again, that's why it is a noise type detector. Next one. Will similarly we can go for all possible d min minus 1 combinations. Okay, and that's your simplified generalized decoder. What we have proved theoretically, this preserves diversity, and your diversity is d min. So based on this, it's the first time that other than grant doesn't claim preservation of diversity, but it is universal. It also applies to all possible codes. So our decoder also now applies for all possible codes, because given your G and H, we don't need anything else from the code word. How you designed it is your problem. Okay, what we are concerned with is the decoder. And you can see in this example here, we have applied our decoder to VCL 1574. It has a minimum of 4. So we'll flip 3 possible errors, right? So we permute it. Then we segregate into LRB, that is, okay, so there's one typo here. So D min is 5 actually for VCL. And we'll add noise in all possible combinations of 4 bits. Does anybody recollect any decoder for BCH codes? Yes, they won't teach you that in digital communication. It's in coding and decoding. So anybody aware of any decoder for BCH codes?
Participants, if anybody has already gone through the encoder and decoder for BCH, they can raise your hands. If you are a little bit shy to share your thoughts or your learnings, then at least you can raise your hands or you can put some reactions. Let's make it an interactive session. So, sir, I guess you can please continue.
Yes. So that's what is called as there are two. They are algebraic decoders. There are order of complexity is n power 3. So for a 15/7 BCH code, your decoding complexity would be 15 power 3. That is, come on, you can say at least this much. 15 power 3. 10 power 3 is,
Come on, participants. Professor is trying a lot. Please respond either by mic or by typing in the chat box. Please be active. I guess he's not enjoying delivering the talk. Yeah, there is one message in the chat box, sir. Shall I read it for you? Professor Zafar, are you there in the meeting? I think his screen is just frozen. Hopefully he will recover from the glitch. So participants, I think he needs some, water or something. So he has just taken a break, just a short break. But you please do not leave the meeting. He'll be right back. You just stay tuned. And one just humble request to all of you. Sir is so experienced. He is just a huge amount of knowledge he is having, and he is with us. He's sharing his experience, his learnings, his teachings with us, and you people are not responding to him. So I personally feel that he's not liking it. He'll be back. He'll be back. He's just taking a short break. He'll be back within 1 or 2 minutes. So you just stay tuned. But let's be a little bit interactive. If he's asking 10 raised to power 3 is what? You can calculate it as 1000. Simple. You can drop it into the chat box. So he'll be right back. Please stay tuned.
Apa tuh now?
Hello.
Yes, sir.
Yes.
Is everything fine, sir?
Yes, everything is fine.
Yes, sir.
So we have a power cut at this particular time. So I had asked
Oh,
Professor Taka for a break at this point.
okay,
Anyhow,
okay.
uh, yes. So coming back, BCH
Yes,
codes complexity is very large, and even if you take 10 power 3 is 1000, right? 10 power 15, 15 power 3 is anyhow. So the complexity is huge. In contrast, we are doing 2 power 4, that is 8 possible combinations. Okay, and in this particular case, I have shown you all possible combinations, right? All 16 possible combinations. You see the most reliable part, there is no change. We are not doing any test there. The least reliable part, we are checking all possible noise patterns. Okay, so we have seen this for very previous example also. So one pattern doesn't work, another pattern it does work. So that's the decoded code word. What do you get? See this,
yes, sir.
right? So
Right.
your hard decision decoder is somewhere here, which is very complex. Okay, and most of your satellites actually use BCH codes with this particular decoder. Okay, so what performance you would get, that is 10 2 into 10 power minus 3 at around 24 dB. We are actually getting the same performance at 17 dB, right? So
Sir,
78 dB.
sorry to interrupt, but one query is there from one
Yeah,
of the
yeah,
participants. Shall I read it for you?
great, great. At least
Sir,
somebody is there.
this is yes, sir. The query is what coding and decoding strategies can help reduce energy consumption in 6G communication systems.
Well, I think mostly you were not there in the start. The strategies for coding and decoding is essentially low complexity. You want a low complexity encoder, you want a low complexity decoder. You cannot have high compute power because these are all digital, right? Both coding and decoding are digital. Modulation, you have no choice, you have to put it anyhow. So the energy saving strategy for coding and decoding is have low complexity encoding and low complexity decoding. Okay, and our approach, we are saying that just 8 flips for BCH codes. Okay, d min minus 1 flips. So as long as your d min is small, and for coding you won't need a diversity order of more than 8, right? No, I am not aware of anybody more using 8. Massive MIMO diversity order possible is huge, right? But nobody does more than 8. Rest of it, they said, I don't need coding after that. Okay, because that's where your curves begin to saturate. So a diversity order of 8, if you take, and in our case, that will be 2 power 7 minus 1, that would be around 127. Okay, so 127 possible combinations, you'll get the best possible diversity order. So it is, our approach is really very low complexity, and you can have large, more importantly, you can have large block lengths. So whatever block length is possible, you can use it. So it's really very useful from the energy perspective because you are not using a lot of compute power. I hope that answers your question.
Yes, sir. We can continue. I hope you got the satisfactory answers.
And
And if
more
anything
importantly,
else
if
is
you
there,
can
yes,
see from this code, okay, if you are this particular example that we are showing here, okay, with hard decision decoding, you would be somewhere here. You are able to see my pointer. You would be somewhere here. That is 24 dB. You are getting a bit error rate of 2 into 10 power minus 3. That is your target. What we are getting is the same performance at this particular point, which happens to be 17 dB. So you are saving 7 D, you are getting the same performance at 7 dB. So that means a saving of energy of the order of, see, 3 dB is half, 6 dB is 1/4. So more than you require 1/4 less power. That is when, if you are going to transmit without doing our decoding, okay, you are doing hard decision decoding, you would be here, right? So you would be required to transmit 4 times more power. So while the reason is we are preserving diversity order. Okay, so the saving in terms of performance because of saving of diversity is huge. Okay, so
Yes, sir. I think the participant got the answers. Otherwise, he can drop his queries in the chat box, and we will address at the end of the session. You please continue with the
yes, I
talk.
can do that at the end of the session.
Yes, sir.
Right? So this was for PCC, and PCC was never used for a decoder. So this allows you to use wherever you have simple parity check codes, and in fact all Macs have parity check codes. So that actually doubles your diversity. It multiplies by 2. This is for Hamming codes. This is for BCH codes. I have some results for polar codes also. Okay, so I think I have conveyed the main message. So decoding now, what we expect for 6G is flip noise vector smartly. Don't use brute for decoding. Do it smartly. That's the message till now. Okay, and these are various codings that gains compared to different codes. So I'll skip all this because this is maths. And this comparison here with grant, you see we have significant advantage as compared to grant because they don't preserve diversity order. They have a more complex version that is called as threading grant, but we still have a better performance compared to that. Right, and this is the complexity curve. There is no comparison in terms of complexity because everybody else is significantly more complex. We are way down below here. And we also did some more work and to plot coding in versus diversity, and that again we are all these results are significantly in favor of our decoders. I'll skip these plans and then go into the next idea. What do you think we can do more to actually improve the performance? Based on the ideas that I have been given till now, what do you think we should be doing now to improve the performance further? Well, till now we are flipping the d min minus 1 least reliable bits in the LRB, right? That was the idea till now. Now, if you want to trade some complexity and get some more coding gain, what we can do is extend this window. This LRB, I can extend it with this window to the right. So we have more LRBs and less MRBs. Of course, that will add complexity, but it will it will try to get some of the coding laws that we are getting as compared to soft decision decoding. This is your soft decision decoder. Okay, so as you increase the size of your yeah, wait, let me go back to, so that was the concept for extended diversity flip Victorer. We are extending the LRB by an factor epsilon. So rather than say 4, I add one more bit, 5, 6, depending on E. So we have put a new value. This gives us a, if I make E all the way till 15 here, so that would be same as soft decision decoder. I will be checking for all possible combinations, right? and it would be worse than soft decision decoder, because there the number of code words would be 2 power k, and here I am doing 2 power n combination. So while it would be same performance with soft decision decoder, there will be no coding loss, but uh, you'll pay in terms of complexity. So there, by putting this new parameter epsilon, we are actually trading. We have introduced an approach of trading now the coding gain for complexity. Okay, so this is shown graphically here. So we add one more bit here, two more bits here, three more bits here. The complexity increases. What you get is a better coding gain. And so we plotted the coding gain that you get for various epsilon. So you see, as epsilon increases, course, it begins to saturate after a certain value. Okay. So performance get better as you increase the value of epsilon. And what's the complexity for epsilon is equal to 3? It was 3 plus 5 plus 3 is 2 power 8. So it is still reasonable. You are doing 256 comparison. So till getting diversity order D, that is d min minus 1, the complexity was really simple. But getting more, you are increasing the complexity significantly for small gains actually. Okay, got that idea? So we then added another approach. What we said was, we will add another variable, that is, uh, we'll not try to preserve the d mean. Also, we can make that also flexible. Somebody may want to have a smaller diversity order, that's also fine. So what we did was, in the extended window, we'll only flip delta bits, all possible delta combinations. Okay, so that was the third extension that we did, and it's a graphical representation of that. Anybody is interested, wants to ask questions, I can ask that, otherwise I'll skip this. So I've given you the main idea here.
Okay, sir. At the end of the session, I think they will ask. Please continue.
Okay. So I'm skipping this, and what you can see is, based on the different parameters, alpha, beta, delta, that we have now put into the decoder, you trade the complexity to get a better performance. And this particular code actually is near optimal for various wavelengths. I'll show you later on. So what you see is, as the extension variable increases, the performance increases and then decreases. So the optimal region of working is somewhere in this region. You don't need to increase beta too much, right? And you see, it's just 1, 2, 3. So for a BCH code, that's very good. I'll skip the patterns. You are available. They are known and available. There's a third thing that we did. We said was, there's something called log likelihood ratios. Okay, rather than using the channel coefficient head, we can work with log likelihood ratios and a weighted sum, and that actually is from the Orgrand approach, and that also gives a significant factor in improving the performance. So those are the results for log likelihood ratio. You see that the curve improves further. So essentially, depending on what application you are working for, if you are working for URLC, you can maybe say trade some performance for the decoding. Uh, you can trade some compute power for getting the desired power. So you can go for a better values of alpha beta. If you just want bare minimum, that's also is possible. You don't pay too much to get a good decoder. So this approach now allows you to have a decoder suitable for your applications, which was not available till now. So the various use cases of 5G or 6G, now for a different use case, you should actually use a different decoder. That's now what we are saying. Okay. And
Yes, sir.
here
It's
you
okay.
can, yeah. So basically here you can see is a beta value of 7 or 8 would be good enough. In fact, 8 is actually, that's all what the maximum possible length for beta, because now it would be equal to n. Beta plus alpha would now be equal to n. So you cannot have more than that. So, but what you can see is 5 itself is good enough. You would have 4 somewhere here and 3 somewhere here, 3 and 4 somewhere here. So really you don't need to increase too much. Okay, so that's why I'm saying, so you can choose a value of alpha beta depending on how close you want to be with your soft decision decoding result. For 15,7, it's possible you can do the simulations to get the soft decision decoding curve. We have put it here for comparison. And you can clearly see here, based on number of code book queries, our code is significantly better. Or grant, they have not tuned the parameters for our grant, but it is somewhere here. But ours is still better. Okay. And the possible region to work is somewhere here, where you actually start, don't get, you have to pay too much to actually get a small gains. So this is the region you should actually be working in for most of the use cases. I'll skip this and I'll skip this also. The important difference as compared to MIT contribution is we preserve diversity. They don't guarantee diversity. We give a tunable performance for the decoder, so they are applicable for different use cases separately, which is not possible for other decoders that are available. And of course, as in the case of Grand and other, this is a universal decoder. So as you have seen, the same approach is working for PCC, which never had a decoder, for Hamming codes, for CRC codes, which didn't have a good decoder till now, right? And Hamming codes, PCH codes, we have some polar codes, but I won't show you that. There's one last final idea that we have been proposing here. What we said was we are flipping the least reliable bits. What we can actually do is flip use the most reliable bits, and from the most reliable bits, generate the least reliable bits. Okay, and this idea, even though it looks simple, is not so simple, because you have to use a matrix inversion. So it is complex, and the traditional name for that is what is called as OSD, ordered statistics decoding. Okay, so it is better than soft decision decoding because it reduces the complexity. Not good enough for practical applications. So what we said was we'll use the OSD approach, but we'll still guess the ordering rather than uh, flipping all possible uh, MRB bits. What we'll do is, among the most reliable bits, we'll flip the least reliable. That was our approach, and that has made OSD also very, very useful. I won't show you all this because you won't understand OSD. So I won't. I've just given you the idea. Anybody is interested, we can discuss after the talk or offline. Okay, so I'll not go into all these things, but the idea basically is this: OSD would flip the combinations use the MRB to get the LRB. What we are saying is, in MRB also, rather than trying to work with different combinations, we'll use or we'll flip the least reliable, and that has given significantly important better results. See, we are actually now touching soft decision decoding curve. Okay, and I think I'll skip the hybrid encoding scheme also. This one we have been pushing for 8.0.15. We are saying that there is a better decoder, code and decoder based on both the coding and decoding that we have. I'll skip that. We are basically proposing an extended Hamming code for the CRC in lieu of the CRC, saying that it gives us a significant advantage. But that's for some later use. Okay. Uh, so lots of works to do. Application of these decoders in turbo, LDPC, etc. is something that that's the traditional coding area that we have not tried to use. We have been working, trying to come to the weak point, that is for which the coding community doesn't have an advantage or doesn't have a clue, that is for short block lengths. So working with that, we extending it to the traditional coding areas of large block length, and still showing that for fading environment it works. That's some work that is left. Okay, application of our flip approach with the turbo or iterative decoder, that's something that should be looked at. Right. So I'll stop here and start taking questions, please. You want to see the references? I have shown the work. I think I am not put it here. Somehow I missed it, or anyhow, I have shown you the 8 uh, uh,
Hello, hello,
publications
sir.
that we have, and 3 conference papers and 3 patents. So if you want, I can put that up again for you right at the start. So with that, I will start taking questions, please.
Yes, sir. One participant, I think he already just put his question in the chat window. How can general framework be designed for ultra reliable communication in 6G, balancing complexity and performance? This is the question.
Yeah, thank you, Nagarajan, for the question. I think the previous question also was from you, and it was in similar lines. See, for ultra reliable, you need to use good codes, and codes that actually are optimal. Okay, in that they achieve the D-mean, that the decoding complexity possible for given N and K is Reed-Solomon codes, certain Reed-Solomon codes, right? Till now, they are not been useful because their decoders are very complex. Our decoder makes it available. So what we are now targeting, and we would actually be wanting to work with some of the companies who are putting up uh, proposals for the standards, is we would want to say put up Reed-Solomon codes, we'll define how to decode it, and it would be really very useful. That's what is our approach. Okay, so based on our decoders, what we are saying is use the best possible codes. We'll give you a decoder.
Yes, sir. I think one more, sir. One more question from Nagarajan. How can a generalized framework incorporate real-time error correction to reduce
Well, this
packet
is
loss in
real
high
time.
mobility
See,
scenarios?
if you want a diversity order of 3, we are doing 8 flips. That doesn't take any time at all. Okay, so it's our decoders are basically real time. Somebody wants to put a GMU, he can do that. Okay, so we'll see whatever complexity you want, we can enable that, because for ultra reliable, you really are not looking at how much energy is being consumed. So in that case, we'll say we can still save energy for you with a significantly less decoding complexity. Okay, so go with the best decoder, best code. We'll have a corresponding decoder that meets the requirement. That's the answer.
So, any other questions, participants? Yes, one more question, Professor.
Well,
Can
that's
different
not
coding
possible.
technique?
You cannot have different coding techniques to be used together at different stages, because standards typically have this side, or at least what I would say is till now they don't do that. you have to, at the start of the session, you have to say whether you are using polar port or turbo port, or you are using a convolution port, or whether you are using the 8 repetition port. You have to say right at the start. You cannot shift in between. And most while standard says you can use one of the possible decoders, application wise, chips, when they design the SoCs, they really fix one of them. So I am not aware of any chip that can do all possible, say LDPC and turbo together, or polar boards together. So typically they go by one approach only. We are not saying that our approach is very different from AIML. AIML would come up, say that we'll use various decoding data available to come up with a decoder based on the use cases. For our case, the target that we are giving, IoT or URLC, you really don't have time for doing all those things. Okay, this is one application where AI/ML is really not suitable. You don't have the time to do either, or the energy for the time to do for URLC to do AI/ML, and you don't have a time, you don't have the energy to do AI/ML for IoT. Even though people are proposing, but I don't see any use of AI/ML for these use cases at least.
Participants, if you can please ask some question. I think Professor, it's it's okay. It's done. So Professor Jafar, hello Professor.
Yeah, I'm there. I'm there.
Yes. So Professor, thank you for sharing your invaluable expertise with us today. Your insights were truly enlightening. So thank you so much.
Thanks a lot. And then any questions? I have put my email address also. I'll type it here also in the chat box. You can get in touch with me.
Yes, Professor.
Right, I have put here in the chat box. Anybody has any questions, you want to link up, discuss ideas, you are welcome.
Yes, thank you, Professor. Thank you so
Thanks
much.
a lot. Bye.
Yes.
Good night.
Okay, bye. Have a good night. Okay, bye. So participants, you can wait here. Our next expert will join soon.
Hey, hi Arvind, Sanjay this side. Are you able to hear me?
Oh, yes, Sanjay ji. I can hear you.
So what we will do is they have just finished the session. We can just take a quick 5 minutes break. I also finished one of the meeting here. Maybe we can resume at 7:35.
Okay.
So let's start at 7:35.
Okay. After 5 minutes, we will wait. Okay.
Sure. Thanks. Hello, Dr. Soumya. I hope you're able to hear me and able to see me.
sir, ruko. Yes, sir, I'm here. And
I hope you're able to hear me as well.
so how are you, sir?
I'm doing good. I'm doing good. Great.
So I think no more introduction is required.
I think we have already had it for 2 times, so it's not required.
Exactly.
Yeah.
So audience and you are already in communication from last 2-3 days. So without any delay, can we start? And if you want to discuss anything or over the assessment or feedback of the previous sessions.
Nothing as of now. Actually, I was just, a little tied up in few things. So maybe I'll share the results with you offline, and I will also share another assessment with you tomorrow morning. Right. I was in the training. I was in the training for whole day today as well. Right. So.
So how was your training, sir?
Yeah, going good, going great so far. Yeah.
That's great. That's great.
So
that is how you keep yourself updated. You go for the training sessions and keep yourself updated. Very nice, sir. I really appreciate. So without any delay, let's start the talk.
Okay. So can you make me the presenter so that I can share my screen?
Yes. Just a second, sir. I'm just making you presenter. Can you check?
Not as of now.
Now?
Yes, now I can see that.
Yes. Okay, sir?
Yep.
So
let me just share my screen.
Yes, sir.
Okay, so I'm just stopping my video for saving the bandwidth for everyone. Okay, great. Okay, greetings everyone. Dr. Soumya, just to confirm that you're able to hear me and able to see my screen so that I can get started.
Yes, sir. Clearly audible and slides are clearly visible.
Okay, great. Good evening, everyone. Again, we will continue with the discussion what we have done yesterday, right? So yesterday our discussion was mostly around talking about, first of all, we started talking about the evolution of telecom network, where we talked about the history of the telecommunication network starting from the days of 2G to 3G to 4G to 5G. And we also talked about how this evolution is moving towards the native AI architecture. Now, even before we talk about native AI architecture, we also have used this similar terminology in the previous generation, where we talk about something called as cloud native. Now, even before we talk about AI native, let us try to understand what do we really mean by native, right? What do we mean by native? Let's take an example. Let's take an example. Let's say I want to have a cake which is having a taste of chocolate, right? So I'm just taking an example of a cake where I want to create a cake which has the taste of chocolate. There are two ways to look at it. First, you create a plain cake without having any chocolate in that, and on top of that you add a layer of chocolate. So normally we see that these cakes and all, they have a layer of creams on top of it, or maybe some fondant and other thing. So this is just the chocolate part of it, and this cake inside has absolutely no flavor or no taste of chocolate. Now, in addition to this, I may create another cake where chocolate becomes the main ingredient of, or the flavor or the taste of the chocolate is the part of the cake itself. Now, and this is nobody's guess, right? So we know this cake is going to be tastier than the cake what we see here. right? Because this cake will just have a layer of chocolate, but inside that it will be just a plain taste, right? But inside this, there will be taste of chocolate in each and every bite. Exactly, that is the difference between the AI enabled and AI native, cloud enabled and cloud native. And that's what I wanted to convey here. Now, when we initially started talking about telecommunication network, we told that the 5G workloads are going to be deployed on the cloud architecture. But if we remember, the cloud was initially designed and created for the IT workloads, not the telecom workloads. It was not designed for IT, not designed for telecom workloads. Similarly, 5G was not IT. They were mostly purpose built hardware and purpose built software. So all these telecom networks, till 4G, I'll not say 5G, till 4G, they were all purpose built hardware and software, which is coming from the vendors like Ericsson, Nokia, Huawei, ZTE, Samsung, etc. However, when we started talking about 5G, we wanted all these 5G telecom workloads to be deployed on the cloud architecture. Now, traditional cloud architecture revolves around virtualization, and we typically refer this as VNF. But over the period of time, we also realized that VNF may not be a great option when we want to scale to the telecom workloads. And that's where we started moving towards the CNF kind of architecture, where we talk about containerization or cloud native network function. So what are the key criterias of the cloud native architecture? Cloud native architecture where we talk about containers, which are typically created with the Docker kind of options. We have orchestration, which is typically done by K8s. K8s stands for Kubernetes, where 8 is the number of letters between K and S, right? And this is a Greek word which comes from the the person who steers the ships who are carrying containers in the sea. On top of that, we have terminologies like DevOps, microservices, CI/CD. So all these things became major ingredient of the cloud native network function, and later they evolved into another term which is also called as telco cloud. So from the world of cloud, we move to the cloud native, and from the cloud native world, we move to the telco cloud. What is telco cloud? A cloud infrastructure, which is designed for telecom workloads, because telecom workloads are very different than the IT workloads, right? So this is how we have seen the journey from the cloud to cloud native to the telco cloud. Similarly, initially, when we started talking about SON, self-organizing network, and if you look closely to the most of the things related to SON, they were more or less targeted towards the radio access network. There was absolutely very minimal automation happening in the core network. If you look at the features of SON, you will see features of SON as ANR, automatic neighbor relations, MDT, minimization of drive test, or maybe self-healing, self-optimization, self-configuring. But most of these features and functionality were evolved around radio access network, right? So the kind of ideas what we had some applications. So there is a hardware of the network. On top of that, there is a software which has nothing to do with the AIML. And on top of that, we have a separate application related to the automation or the orchestration. Now, all these were created as they were all created as separate silos, and they were not very effective. Now, in case of 5G, we try to implement some of these things along with the bringing in this AIML inside the software architecture of telecommunication network. And even then, this is not really the integral part of 5G. So basically, 5G is also having this AI ML thing as a topping, not as a main ingredient of the complete recipe. Now, what we are trying to do in 6G is, that 6G is going to be a part of each and everything what we discuss in the future network, starting from the hardware plus AI, talking about software that is also enabled with AI, talking about chipsets, they are also with AI. The applications for the end user, they are also going to be the AI. So all these things what we are discussing, starting from the hardware to the software to the chipsets, and even going to the applications, they are all enabled by artificial intelligence. And that is what we are talking about as a native AI architecture. So the applications which we are trying to build, they themselves are built with the perspective of the artificial intelligence, machine learning, Gen AI agents, etc. Of course, some of these terminologies are relatively new to the world, and it may take time. It may take time to actually get all those things on the ground. But this is the kind of approach we are looking for the future generation. So starting from the channel estimation, going to the level of resource allocation, edge computing, talking about network exposure functions, that where we actually expose the API of our 5G network to the external world. Each and everything can be enabled, can be empowered with the artificial intelligence kind of activities. So that's what we are looking at in the 6G network. Now, even before we talk about it, let's see what is Gen AI. We already talked about this yesterday. Gen AI is generative AI, which is capable of creating some kind of content. Right. Now, this content doesn't mean that it has to be some kind of video, audio, picture. It can also create a lot of content to provide new solutions to enhance your telecom services as well. It can actually provide some kind of personalized experience for the user. Now, let's take an example. We, as a telecom user, we have CDRs, and nowadays they are also referred as XDRs. C stands for call detailed record. So everything what we do on the call, whether we make calls, voice call, video call, SMS, data, this incoming call, outgoing call, whatever we are doing, it is recorded in a detailed file, and the detailed file is either called as CDR or XDR, call detailed record. And this is not new to 4G or 5G. It is from the days of wireline network itself, from the days of wireline network. Now, if I look at these CDRs, and if I try to analyze these CDR with my large language models or large telecom models, and we use some procedures like LSTM, long, short-term memory, right? By doing all kind of things, I can create some kind of personalized bills for the customers. I can create personalized summaries for the customer, right? I can try to create some kind of, try to do some kind of fraud detection where I see there may be some fraud which may happen. So these are some of the use cases. The use cases can be related to network, or in network also, it can be related to network optimization, maintenance. It can be related to the PSS system. It can be related to the customer support. It can be related to order management as well. So there are hundreds of use cases which can be enabled, which can be created by implementing AI, ML, Gen AI, LTM, etc. So these are some of the things. We are exploring in 5G already, and it may go exponentially in a big way in the 6G network as well. Now, what type of benefits we are getting out of it, and how telcos are evolving in the world, right? Now, to understand this, there is, I keep on getting a request from few companies. They say we are transitioning from a telco to techco. So this is one of the key, term what we are using, what we are hearing today, telco to techco, from a telecom company to a tech company, digital company. That's what they're trying to do. If you see in the past, the telecom company used to sell the SIM cards. So their only thing, the only business model was to sell the SIM cards to more and more and more users. However, today, that is not sufficient for them to stay afloat. They need to get into more services. They need to bundle a lot of new services with their offering, and then only they will be able to stay afloat. Similarly, they're also getting into a lot of business related to enterprise. This enterprise business can be related to some kind of private networks, where I create private networks and sell it to the industries, to academia, and a number of other things. The network slicing as a service, what we talked about, or some kind of MEC services, what we discussed earlier. Now, so we are not really referring, or not only referring to the retail customer as a customer, we are also trying to reach out to lot of, lot of enterprise customer to generate more revenue streams. These things will require a lot of intervention of AI/ML. Now, these things are possible. These things can be extended only when we do lot of implementation of AI/ML in these kind of scenario. So all these new use cases what we are talking about, and these may be extended to many use cases in the future generations, and that's where this becomes a main fuel in the growth of the wireless network. Now, what are the key AI technologies which are enabling autonomy in the 6G network? And we will see that in a demonstration at a slightly later stage, right? So we will be creating one particular ML model. We will be training that model. We will be testing that model, and then we will see, how this can give us some prediction related to the resources which should be given to the different slices. That we will see in the demonstration slightly later. Now, we can use machine learning. We can use machine learning for creating some kind of adaptive models. How do we do it? We will talk about it. We can also talk about deep learning, where we can look for complex pattern recognition. If you remember, when we talked about machine learning types, we talked about supervised learning, unsupervised learning, self-supervised learning, reinforcement learning, and we have seen some specific use cases for each of those different category. So there can be different type of categories, different type of use cases which can be satisfied by different kind of technologies in the AI/ML world. For example, reinforcement learning can be used for self-improvement in the network functions. So these are some of the examples. At a later stage, we are going to see some of these examples in a detailed fashion as well. Talking about AI native architecture, as I have spoken just few minutes back, that's what we are referring to. So AI is not really merely coming as a layer or as a topping in the 6G world. It is talking about AI integrated as a foundational. So it's a part of the main ingredient. It's not just the topping, it is part of the main ingredient itself in the 6G network. Now, SON is something what we have already talked about. SON is more about the automation in doing the network configuration and traffic management. so, so basically, just give me a second. So basically, what we're trying to do, majorly these network management things used to happen with a lot of human intervention, right? But what we're trying to do, the way networks are growing, we want to reduce that human intervention by bringing in the automation in the dynamic environment. Why this is required? Why this is required? Let's try to use this as an example. 1 second. Okay, right. So let's take an example of the things what we were discussing earlier. I was talking about 3 service verticals: EMBB, URLLC, and MMM. MMTC, massive machine type communication. Now, here my expectations are to get 20 Gbps peak data rate and 100 Mbps user experience data rate. Now, the same requirement in the URLLC is the latency lesser than 1 millisecond and the reliability as 99.99%. That is the downtime of 5 minutes per year. 5 minutes per year. That is the kind of reliability we are looking for. In MMTC, we are not looking for higher data rate. We are not looking for lower latencies. We are talking about millions of devices per square kilometer. Now, try to understand the kind of KPI requirements, what we have got here are very diverse. And achieving these kind of KPIs with the manual intervention is impossible to do. It is impossible to do in the network. Then how do we really do it? To do this, we have to bring some kind of dynamism in the network. And when I'm saying this, please don't think that this is coming as a rocket science. There was earlier lot of different features which were there in the network, and now we are trying to create a beautiful packaging of that, and then we are trying to build it together. To take an example, we already had something called as quality of service in the previous generations as well. We already had something called as MORAN, multi-operator radio access network, or MOCN, multi-operator core network. We had something called as DECORE, which is called as dedicated core network, or EDECORE, enhanced dedicated core network. In the transport networks, we already had things related to VPN, virtual private network, maybe L2 VPN, L3 VPN, IPsec, RSVP, which is typically called as traffic. We also do something called as traffic engineering. So there were a lot of different things in the radio network, core network, transport network. By bringing in network slicing, we are trying to create a beautiful packaging of all these things. Of course, network slicing is not going to remove all these things. These things will become subset of the network slicing. So these things were mostly available on the best effort basis. But network slicing provides a SLA driven isolation in the services. Now, what is SLA driven? SLA means service level agreement. That means if I create these isolation, I can also offer these kind of services to the enterprise customer as a value add services, and I can adhere to their SLAs. So that is what I'm trying to target by creating these kind of isolation. These things are possible when we are trying to meet these KPI requirements separately, and these separate sections of the network, separate logical sections of the network are completely isolated from each other. That is the kind of target what we have, and that is impossible to achieve in the manual with the manual intervention. It can be done only with the AI ML intervention. Without that, it is impossible to achieve. So these are some of the key areas where AI ML is going to play a major role. Similarly, when we talk about multi-access edge computing, MEC, or multi-access edge computing services. Most of these services, we will have the AI running on the edge. We will be having AI running on the edge, and then only these applications will make sense. Right. Of course, they come with their own challenges. Application portability is a challenge there. Implementing these infrastructure, these compute in the network architecture itself is challenge. And there are some solutions which are being built around these things. Let us take an example. So, for example, one of the leading operator in the US which is called a Dish Wireless, they have deployed their complete infrastructure on AWS. AWS, Amazon Web Services, and the Dish network has deployed their complete infrastructure on AWS. But how do I really deploy CUDU, which is typically the part of the radio network, along with the UPF or along with the MEC? So AWS has come up with a on-prem server called as Outpost. So if you Google for Outpost, you will see a server which is sold by AWS. So it's a server which is enabled with AWS application, AWS services, and can be sold as a server to the operator. So this Outpost, what you see here, can be used for hosting your CU, DU, near real-time break, your UPF, MEC application, and along with some kind of local AI ML models. These are the kind of architectures we are looking at. So Outpost, Outpost is one of the server rack coming from the AWS. And you see, this is very ironical. Now, when you look at AWS, and whenever I talk about AWS, the main motto or main punchline of the AWS is, okay, why you want to buy servers? Host everything on my cloud. And now they themselves are selling you the servers. Right. So basically, all these things, and these companies like AWS, Azure, GCP, they are all called as hyperscalers. What is the meaning of hyperscaler? That they can scale your network capability, they can scale your applications at a hyper level. Overnight, you can go global. If you want to launch your services, any services in US, you can do it overnight. That is the kind of scale we are talking about. Even hyperscalers are playing a very important role. Even hyperscalers are playing a very important role in the journey of the telecommunication network. Just to take an example, AWS is offering something called as 5G private network. So if you go to AWS console, and let me show you this with an example. So I just go to AWS and I will search for AWS private network 5G. Now you see this private 5G network, which is offered by AWS. So it talks about a lot of use cases, how you can get started with this. So they've recently changed it. Earlier, they used to have a complete life cycle of, how do we really do the setup and things related to that. So if I click on Get Started with AWS 5G, they will ask you to log in into their console. So you can go to console, order for a private network, and can start using it. So this is the kind of freedom. This is the kind of So this is the kind of freedom, and these are the kind of options what we are looking for in the future. And that is only possible when our networks are enabled, network are supported with the AI ML kind of architecture. Now, the next area, and this was one of the questions which came from someone, what are the different 6G use cases and the research area? Frankly speaking, the kind of world I come from, I don't really, traditionally, if I talk about, I were never involved into these areas. I used to start working with the technologies when the standards are being made. I was never involved in my previous roles, maybe 3 years, 4 years back. I was never involved into these areas. I start working on it when the standards are in place, and then we start talking about the technologies and the deployment of that. However, in last 2-3 years, I have communicated with a lot of people who are working in the research, working in academia, attended a lot of conferences, and by bringing all those information together, and of course, these can be, you guys, you are working in academia, working in research, you guys know much more than this, much more than me on these topics. But I'm just trying to summarize the things what came to my mind, and maybe you can add more to it at a later stage when we open for the question and answer. Now, what are the different areas, 6G research area we are talking about. One of them is terahertz communication, right? Now, even though this terahertz communication is shown as a superstar or a very promising area, we also need to learn from our experiences what we had with the wave, millimeter wave. I'm sure you are already aware about two different frequency range, FR1 and FR2. FR1, which ranges from 450 meg, goes up to 7.125 gig, and another one which starts from 24 gig and goes up to maybe 52.6, and later it was extended up to 114 gig. Right. The FR1 and FR2, these were the two spectrums, I'll say frequency bands which were defined for the 5G network. And this FR2 is also referred as millimeter wave, and it comes with its own challenges, right? Because the kind of kind of bands what we are using in millimeter wave are very high, and they have lot of challenges. And today also, if you look around, there are very few, I'll not say it's completely a failure, but there are very few success stories around wave. There are very few success stories in wave. If you look at even at the best phone, if you look at the iPhone 16 also, you will see that it comes with a very limited support of millimeter wave band or FR2 bands. So even though it is defined as a technologies, the overall support is not that encouraging even in the millimeter wave. We are talking about the terahertz, which will go beyond 100 gigahertz. Now, managing all these kind of transmissions and doing these kind of transmission at terahertz frequency is not going to be very easy. Of course, it can happen. Of course, it will come with its own solutions, but it is not that great. It is going to have its own challenges. So what is the sweet spot for the spectrum for the 6G? Of course, they are going to continue with the FR1 and FR2 band. But other band, and somewhere unofficially they also refer it as FR3 band, and they also call it as a upper mid band. Upper mid band, the band between 7 gigahertz and 24 gigahertz. Starting from 7 gigahertz and 24 gigahertz, that is what is called as upper mid band. And that is a sweet spot and the trade-off between the capacity and the coverage. So this has best of both the worlds. It can give you better capacity. It can give you a better coverage than millimeter wave. So this range, the range between 7 gigahertz to 24 gigahertz, is going to be a sweet spot for the spectrums for the 6G. That is one of the area we should target. Of course, talking about native AI integration. So AI has to be a part of each and everything in the 6G network. Talking about quantum communication, that's not really my key area, my strength area. I may not be able to talk much about it. Quantum computing, quantum communication, these are some of the areas which will be required to have a very strong infrastructure and the hardware. Cell-free communication. Now, we have already talked about MIMO, multiple input, multiple output. We have also talked about MIMO, massive MIMO. There are some definition around extensive or extended MIMO, right? Multiple input, multiple output, multiple input and multiple output. But now we're also talking about cell-free communication, where all the antenna units or antenna arrays are distributed in a way where I can create a uniform distribution of the signal strength. That is what we are trying to achieve with the cell-free communication, where network is not designed with a cell, network is not designed as a cell, because traditionally the cellular network, the name itself says cellular network, comes with a design of cell. Comes with a design of cell. So we want to move in an area where we want to have cell-free communication. Easier said than done. Because the cell-free communication may not be easy to implement, for the massive large-scale network. Because deploying these many different antenna arrays in a distributed area and then connecting them to some devices, central APs, that is going to come with its own challenges. Even in the current network, we are facing a lot of these challenges. So even though as a technology, it looks very beautiful, very promising, the deployment may have its own challenges. The deployments may have its own challenges. The next one is IRS or RIS, reconfigurable intelligence services. When I talk to many academia people, many of them are actually working on RIS, reconfigurable intelligence services. And this is nothing where the surfaces, when they reflect something, those signals can be created in a way where they can add on and improve the overall consumer experience. That's what is the purpose of the RIS or reconfigurable intelligence surfaces. This is one of the key area. I have met many many people who are working in academics. They are working on it. This is one of the another key area for the networks. Talking about green and sustainable network. So our network consumption, the power usage, energy usage has to be green and sustainable. That's what we are looking at. We already talked about ISAC, integrated sensing and communication, where sensing and communication is not really coming as an add-on feature. It is integrated in the wireless network as well. Edge computing is already there. We are talking about enhancing the capability of edge computing, right? So edge applications. So most of the new use cases we are talking about, they will require a completely new intervention of the edge computing, and then only it will make sense. Enhance MIMO and spectrum sharing, right? MIMO, we have already talked about MIMO, eMIMO, mMIMO. We're talking about enhanced MIMO and spectrum sharing. This is another key research area. Where we are talking about MIMO and the spectrum sharing. Of course, the security is a big issue. The way networks are opening up, the security is a big issue, right? And we need more resilient and the secure network. Normally, we call this architecture as ZTA. ZTA or ZTA called a zero trust architecture. Zero trust architecture means we don't trust anyone. We don't trust user, we don't trust device, don't trust visited network, base station, a roaming network, any network. So we designed our architecture in a way where we don't trust anyone, and that is the kind of architecture we are looking at, and we have to further enhance it in the 6G network. Just as an example of this, in case of 4G network, whenever user registered to the network, it is going to send IMSI number. So as soon as somebody is trying to connect to the network, it is going to send its IMSI number. It is going to send its IMSI number. In case of 5G, the equivalent of IMSI is called as SUPI. SUPI, which is called as subscription permanent identifier. So the IMSI number is now renamed as a new name called as SUPI, subscription permanent identifier. But interestingly, we never share SUPI over the air. So whenever I'm transmitting it over the air, I am not sending any SUPI. I'm not sending any SUPI, right? So what I do is I conceal this identity into another identity, and that is called as SUCI. Subscription concealed identifier. Subscription concealed identifier. And interesting, any questions here? Okay. And this SUCI is a one-time use identity. One-time use, it's like your OTP. If you use it once, you can never use it again. So this SUCI is created every time when user has to use it. And nobody the radio network, the widgeted network, and some components of even your home network doesn't know what SUKI is. There is only one device. There is only one device which can convert your SUKI value into the SUPI value, and that is a subs network function of UDM, called as SIDF, subscription identity deconcealing function. So this is the kind of architecture. This is the kind of architecture we are looking for in the 6G, where we want to have our network very, very secure. We want to have our so every user identity, network identity, and interestingly, we also want to make our network open, right? So we are talking about two contradictory things. At one place, we want to make our network open, where even a third party can access the capability of your network, and at the same time, we want to secure our network with a zero trust architecture. And implementing all these things has to be very challenging. It is going to be very challenging. It has to be done properly, but it is going to be very challenging. So these are some of the research area. As I mentioned earlier, this is not really the area I work in. So my knowledge may be a little limited on these areas. You guys know it much better than me, right? So these are some of the areas which I came across after talking to so many different people, and I've just tried to summarize it here. Maybe you can try to add some of the other areas in the chat box, and we can talk about some of these things at a later stage. Now, what example we are going to take? And I'm sure some of these examples we have already taken, right? So, we are recently currently delivering a training program for one of the government company, right, in the telecom world, where we are trying to have a 5 days or 6 days program. And in those 6 days program, we are trying to introduce around 16 different use cases to them related to AI ML in telecom. Of course, not in 6G, but in 5G. And we are doing complete hands-on trainings to them by providing the code, the data set, the complete know-how, how to do it, the basics and the fundamentals of AI ML. That's what we are doing for one of the government companies. Similar things we are doing for one of the leading institute, but which is like, in the grades of IITs. We are doing these kind of training program for them. Now, to take few examples, the AI-driven network slicing. As I earlier mentioned, the network slicing has to be AI-driven. Without that, you cannot even do it. But what do we really do in the network slicing? The network slicing is going to be a dynamic resource allocation exercise. So whenever there is a slice, we have to allocate, because the physical networks are fixed. The physical networks are limited. So out of those physical network, we have to give some of these resources to every slice. And that's what we are trying to do with the artificial intelligence. Now, this particular example, we have prepared a hands-on, and I will be explaining this just after this session. Just we complete the presentation and we will talk about it. So what we try to do here is, we try to do the real-time adjustment of resources for varying service demand. So for example, I can have customized slices for a AR/VR. I can have another customized slice for the IoT. I can have another customized slice for the mission critical communication. And depending on the requirements and the SLAs what I have with the customer, I have to allocate the resources to these particular slices. That's what I'm going to see as a demonstration once we complete this presentation. Now, predictive analytics and intelligent optimization. Now, we can also do some kind of fault detection and prevention through real-time AI model. So there can be a lot of, okay, let me take an example here. So earlier, when we had a, manual fault management in the network, right? So I used to work in the network operations center, and we used to manage the sites. And there was a saying in our time saying that if the engineer in the network operations center is good, it can save, thousands of liters of petrol. What does that mean? So in network operation center, every time whenever there is a failure, we used to get a lot of alarms. And these alarms were typically, sometimes these alarms used to come in number of thousands. But all those thousand alarms were not important. You need to zero in on the one of the main alarm by looking at the network topology. So maybe when you got 100 alarms, maybe one of these alarm is so critical that if we repair this, other 99 will go away automatically. But if the engineer is not good in the network operation center, what he's going to do, he will increase the work for himself, because now he has to inform 10 different engineers, 20 different engineers to do the things. At the same time, all these engineers has to go to the site and do the repairs, etc. Right. Exactly in the similar manner, when all these alarms are appearing, we can also detect the faults, and we can also try to prevent. It may not be possible all the time, but in some scenarios, we can also prevent those faults by looking at the alarms and take some corrective action. So if we are getting some alarms which can be corrected from the remote, corrected from the software, I can take corrective action and I can prevent those faults to happen in the network. Similarly, talking about AI enhanced radio access network for efficient spectrum usage and power management. Please note, this is not really very new to this. I talk about year 2010, the base station used to have a feature called as intelligent shutdown. Intelligent shutdown, where as soon as my battery power goes below certain percentage, I start switching some of my carriers, right? Which was, more of a static arrangement, which was done in the base station. But now these kind of, features can be much more enhanced with artificial intelligence. So these are some of the areas where we may see a lot of new use cases coming in the 6G network as well. Just give me a second. Okay, AI in edge computing, because we have to do lot of data processing at the edge. The whole idea around edge computing, is to process the data at the edge. But how do we really process that data intelligently? That will be powered by AI. So basically bringing in some AI models on the edge, process the data, do some decision making, and then make the IoT ecosystem better. So this kind of use cases are, of course, not limited to IoT services or MMTC services. They can be extended to other verticals as well, but most frequently they are used for the IoT applications. Also looking at security and privacy management with the AI. This is one of the key area where we can use AI-based anomaly detection for cyber threats. Also privacy preserving AI model for data protection as well. So both the data at rest and data in transit, both has to be protected, privacy preserved. That is what we can do with the better AI models. Now, in the network management, zero touch, not trust, zero touch network operation. Zero touch means most of these things are automated. What can be these things? Deployment, monitoring, optimization, and decommissioning. So the network can be commissioned. Even take an example of network slice. Network slice can be created, can be monitored, can be optimized, and can be decommissioned whenever it is not required. And this can be completely automated. And even the end customer, I'm talking, let's take an example here. Let's say you are having a tournament, Indian Premier League, and they want slice. They want a slice which is called as IPL slice. They want that slice to be there in every stadium wherever they have matches. So what I can do is I can create a roster where I say, okay, these are the stadium where matches are going to be there. These are the timings for the matches. And every time when this match is starting, maybe 1 hour before, I will switch on that slice. After 1 hour of that match, I will switch off that slice. And when the IPL is completed, the tournament itself is completed, I can decommission that slice. These are the kind of network operations. These are the kind of life cycle management we can do for the network operation. We can also create some kind of digital twins. This is one of the use case in the 5G as well. Talking about creating digital twins, where we can create replicas of the network for doing the testing, planning, performance analysis, etc. Also, in addition to, so we talk about private cloud, we talk about public cloud, and there is another one which is called as hybrid cloud or multi-cloud. The hybrid cloud is typically the cloud, a combination of private and public. Multi-cloud means a combination of public, a combination of public, sorry, AWS or Azure. So I don't really want to depend completely on AWS. So I can deploy some of my application on the AWS and some of my application on Azure. That's what I can do. So between these two clouds, so that I don't depend on one public cloud environment. So to do these things efficiently, I can have intelligent workload distribution and service deployment across multiple clouds. So I can deploy my services across multiple clouds so that I can have multiple availability zones as well as a DR site. DR stands for disaster recovery site. So if there is a disaster happening, I should have a DR site ready, so my network capabilities are not affected. So just to take an example, a few minutes back, maybe 1 hour back, Chat GPT was completely down. Right. So Chat GPT were having, have lot of different sites, lot of different availability zones, but the impact was so high. So what that happened? So maybe that impact was seen in India. So what they will do is they will switch to a DR site, switch to a disaster recovery site. By the time this India site will come up and running, they will serve this site from somewhere else. So basically, or maybe in India itself, they can have two different zones. One is in Delhi, one is in Mumbai. So they can switch from Delhi to Mumbai or Mumbai to Delhi to avoid any disaster or make these services available. So this Chat GPT was down for about 1 hour or so, maybe from 6 o'clock to 5:30 to 6:30 was not available. So it was facing this kind of problem. So these are some of the key criteria we use in our multi-cloud environments as well. Now, what are the typical challenges and the kind of opportunities we will have? Now, all these things what we are talking about, they are also going to bring a lot of challenges. At the same time, they also open up a lot of opportunities for the research and for the newer gather of jobs. So basically, the data, the privacy and security, which was not really a telecom native thing. I am working from the days of SS7 in the telecom network. And even before that, we had something called as CAS, Channel Associated Signaling, right? And there was zero mention of security. Security was not even a concept in those traditional telecom network. Now, from those zero security networks, we are talking about zero trust architecture. We have come the long way. Now, this brings us to a topic where we have a lot of new jobs available, and there are not a lot of new jobs evolving. And not only the jobs, I'm saying I'm in touch, I'm working with some companies. They are just working on telecom security. There are 3 companies which I know, and the only area where they are working is the telecom security, nothing else. So even security, the telecom network security has become the talk of the town. And as of now, it is only at the early stage. The day we see one of the big operators network is being hacked or being attacked, right, this will go exponentially big. These companies will become exponentially big. So this is the kind of new challenges, so new opportunities which are growing in the market. Now, this also brings us to the scarcity of computational power. Now, when we talk about these AI models and the future telecom network, we will require a huge computational power, and that will also consume a lot of energy. So what we need to do is we need to build the solutions where our AI models are green, sustainable, and energy aware models. So they can run on low energy. They can actually consume lesser energy. That's something what we are talking about. Regulatory and standardization challenges. Regulatory and standardization challenges. So we are looking for some of the regulatory challenges, and they may vary from region to region, country to country, but that may not be easy to implement. So we are looking for some global standards. We are looking for global standards which can actually be used for the AI implementation, right? And this is also sometimes categorized as something called as ethical AI, or maybe responsible AI. They also use another term called as responsible AI, which is responsible for its own behavior. That's the kind of areas, and these are actually, so if you can work in some of the areas related to these topics in for the future generation, that is going to be very very promising area for the future. Now, the of course the use cases, we have already talked about some of them. The XR, extended reality, holographic communication, immersive media, AI as an enabler for personalized and real-time services, collaborative opportunity, and we see a lot of these collaborations are happening where the academia is also coming on the forefront. Now, if we see this traditionally, uh, academia was not really that in sync with the industry, but that difference I've seen in last 5 years. We are seeing some of the startups which are starting from the colleges, and they are becoming front runner in the telecom race, right? So I have many examples which has grown from IIT Delhi, IIT Bombay, IIT Hyderabad, Triple ITB, Comet Foundation in Bangalore. So a lot of institutions which are coming up, and they are fueling the growth of the startups in the telecom research area as well. Also, lot of vendors and operators, they are working on developing and implementing innovative AI solutions. So I'll not say this is not really restricted only to the vendor or operator. Even system integrators, IT, ITES, all kind of companies are a part of it, right? So they're basically developing and implementing innovative AI solutions for the 6G network. So there is a lot of collaboration happening. I'm sure you must be aware about some of these things happening, like Bharat 6G Alliance. We have CBIT, Center for Excellence in Wireless Technologies, which is based out of IIT Madras Research Park. So many of these these collaborations are happening where they bring in academia, vendors, operators, everyone together to create the solutions for the future. Now, before we move to the question and answer, let me move to the demonstration, and then we will quickly summarize the discussion. Okay, so to do all these things, maybe we will not get into the details of each and everything what we are doing here, but let me just brief what we are talking about. Now, of course, there are multiple tools to do it. In this case, I'm using a tool called as Kaggle. Kaggle is again a Google product. You can also, if you want to use, you can use Google Colab as well. So what we're trying to do is, in this particular demo, yeah, please.
Sir, my
Hello?
doubt is, excuse me, sir.
Yeah, please go ahead.
Sir, my doubt is how can we do the network slicing? Either we need to do in the router, sir, like allocating 2.5 gigahertz to some kind of IoT devices and 5 gigahertz to our smart TVs, or like that. We need to slice our network in the router itself, or else it will be sliced at the service provider itself, sir.
Okay. So let me, I'm not, okay, Sri Lakshmi, let me, first of all, before I answer your question, let me tell you one thing, that you have actually mixed 3 technology in your questions. So first of all, you have to be very clear about what you are speaking, right? So you talked about router. Of course, at our home, the device what we see, we typically call them router, but as a technology person, I should not call that as a router, right? That is a kind of set-top box or a Wi-Fi device. So instead of calling it a router, that right word has to be Wi-Fi AP, Wi-Fi access point, right? So Wi-Fi access point is having another functionality which is called as router, and that is not the functionality of Wi-Fi, that is the functionality of the IP network, right? So Wi-Fi is a separate technology, the routing and switching is a separate technology, and the technology what we are talking about, the 2G, 2.4G or 5G, is a different technology. That is one thing we have to be clear. We should not mix all these technologies as a single technology. Now, coming back to uh, the bands what we have got, 2.4 gigahertz and 5 gigahertz, right? Those are the two unlicensed bands which we typically use for Wi-Fi communication, which is also possible, not all of them, but maybe 5 gigahertz we can also use for some technologies which we use in the unlicensed band. So I have a technology called the LTU or NRU, where I can also deploy my LT network, 4G network, and NR network in the unlicensed bands as well. So as of now, the concept what we are talking about is not related to that. Of course, Wi-Fi also supports slicing, but that's not really the topic of the discussion in our in the topic in our discussion. So that's completely separate. So the network slicing, what I'm talking about, I'm speaking from a perspective of wireless network. And in wireless network, we mostly, I'll not say always, we mostly run with the licensed spectrum. So neither your 2.4 gigahertz or your 5 gigahertz or your router comes into play. That's what we need to keep in mind. Now, coming to another topic, coming to another point, in the network slicing, we have multiple components. Typically, there are 5 stakeholders when you provide the network slicing. The first stakeholder is the device. The first stakeholder is the device who is going to use this slice. The second stakeholder is the radio access network, which is going to provide the radio access network resources to the user to use it for this particular slice. The third stakeholder in this chain will come as a transport network. That's where we have, L2 VPN, L3 VPN, routing, switching, SRTP, hard pipe slicing, soft pipe slicing. There are a lot of concepts on the transport network itself, right? The fourth stakeholder will come into this is the core network, which creates separate UPF, separate PCF, separate UPF, separate SMFs, and separate data path, which will connect you to the fifth stakeholder. And the fifth stakeholder is the applications, right? So all of these five stakeholders should be aware about the slicing. Slice awareness should be there with all of them, and then only you can implement it. So basically what we are trying to talk here is all these things what we are talking, that network slicing, even though there are possibility to do network slicing in Wi-Fi, that is not what we are referring to. 2.4 gigahertz, 5 gigahertz is not our point of discussion, because we are talking about wireless network, which is mostly built by the licensed spectrums. Sri Lakshmi, does that make sense? Any follow-up questions you have?
No, sir. Thank you, sir.
Okay. Any other questions from anyone before we move to this? Okay. If no problem. We will take these questions after 10 minutes once we finish this demo. So if you see here, what I've done here is I have used a tool called Kaggle, which is again a Google product. If you want, you can also use simple Jupyter Notebook, or you can also use Google Colab. But all these tools have their own limitation, on their own challenges. Now, in this particular scenario, what we are trying to do is we are trying to create a demo. For the network slicing. And to do this, what I've done is I have created a data set, which is a network slicing test data. So what is this in this data? We will see that in a while. So basically, what we are trying to do is we have uploaded this data set here, and then we have imported NumPy, and then we have imported pandas. So import NumPy as NP, which is used for linear algebra, pandas as PD, which is used for data processing, which is using some kind of CSV file input and output. After running this, it says, okay, what you have to do is, okay, let it run, and then we will see what is happening here. Once it is completed, we have to wait for a couple of minutes. Okay, it's taking longer than expected. Let's wait for it. I'm not sure what happened. It was working a few minutes back. It's when I started the session, I checked it, but that's okay. So if you see, it will give us an output of a CSV file name. In the next step, what we are trying to do is we are trying to read that CSV file, which is uploaded here. And after that, we are using this output, which is shown as like first 10 lines. So if you see, what we are trying to do here is we are trying to have the ID number 1, 2, 3, 4, 5, etc., which is using applications like AR, VR, IoT, or mission critical. And we are talking about the traffic load, QoS requirements, where our critical is, even though it is shown as low, it should be always high. And then what kind of latency requirements you have got, what is the priority level, what are the allocated resources, and things like that. So these are the files which are available in the sample data set. Now, after that, we are defining, okay, what are the slice info? So these are the different, so this data has 7 different columns, which has ID, which has like a integer, then application type, traffic load. So these are the information which is available in the 7 columns, After this, we are importing required libraries and encoding the categorical data. And after that, we are creating a new information. Now, what you see here is earlier, the ID was 1 and application type was something else. So what we have done is the model will not understand what is application type. So they don't understand what is AR, VR, what is IoT. So what we have done is AR, VR is defined as 0, IoT is defined as 2, mission critical is defined as 1. So what we have done is we have converted all these things. In some kind of numericals. After that, whatever data set we have got, we have defined that. Sorry, 1 second. I just went to the next one. We are just defining splitting the feature and the target. So we want to see out of these fields what we have mentioned here, we have discussed here, what are the features? and what are the target. So X is going to be a collection of features and Y is going to be our target. That is what we are going to predict. So what we want to predict here, what are the allocated resources for that particular slice. Now what we are trying to do is it has 2 dimensions. To make it 1 dimension, we are using this command where we have y underscore wi, where we are talking about slice dot allocated resources as a to-do list. And finally, what we are trying to do here is we are trying to split our train data and the test data. So out of this data what we have uploaded, we are saying that the test size should be 25. 25%. That means out of 100 entries, if I have got 100 entries, 75 entries will be used. 75 entries will be used for training the data, and 25% entries will be used for testing the data. Better the data, more capabilities, more clarity you get. And then we are trying to scale some features and things related to that. After that, we are starting the model training. So what model we are using? Random forest regressor is what we are using, and we are using the mean squared error as a metric. Right. After that, we are initializing and training the model. Initializing and training the model. We are predicting on the test data, and then we are evaluating the model. So this method what we are using for evaluating this model is MSE or mean squared error, and then we are printing the mean squared error here. And if you look at it, our mean square error is 396,420.25. So that is very big. So our idea is to reduce this mean square error to the maximum extent possible. After that, we are trying to visualize the things what we are trying to build here. So we have imported Seaborn and matplotlib as a PLT, as a SNS. And after that, we are we are creating a plot with the y-test, which was according to the test data, and y predict what this model is going to predict. And we have used a scattered plot for this. And if we go down here, we see that you may not see a great picture here because the data set is pretty much limited here. This blue line here is actually the value according to the test data. Right? These are the actual values, and these are the values which they have predicted. So this is typically called a scattered graph, where we have some actual values which we are receiving and the values which is predicted by the model. And as of now, you see the accuracy is not that great. So the whole idea of building this model is to make this model as accurate as possible. That's what we are looking at. So similar to this, there can be 10-15 different use cases can be created, different type of methods. Some can be supervised learning, some can be unsupervised learning, some can be based on anomaly detection, some can be based on LSTM or some other methods, right? So there are multiple methods which can be used to deploy and test these models. Similar kind of things we can also do in the Google Colab as well. So this is one of the quick demonstration I wanted to showcase. Right, and with this, what we will do is we will move to our presentation. Happen. Okay, so it's coming up. Just give me a second.
Participants, any questions?
Yeah. Okay, so we are open for questions. If you have any questions, you can drop those questions in the chat box, or maybe you can raise your hands, you can unmute, and then you can ask those questions. I'm open for the questions.
I think there is a one question in chat box.
Mm-hmm.
Yes.
Let me see. Okay, one second. I've just shared my email address as well. If you have any further questions, please feel free to write me an email. Whether ITU don't have any rules for standard regulation. So Suman, if you see, now when we talk about all these things, it is practically impossible to do all these things with a single organization. So what they need to do is the way standards or other I'll say technologies are evolving, right? Which are changing very fast, right? So and doing this with one organization may not work. So ITU has to work with multiple organizations, regulatory bodies, compliances, etc., to make better standards, and that has to evolve over a period of time. So of course, ITU will also have some specific group who are working on it, but they only cannot work on everything. Those things will come with the collaboration of with the multiple institutions. How we can design protocol and make communication between two different layer of different networks? No, Professor Mani, can you please elaborate your question? Somehow I'm not able to understand. What does that mean? Two different layers or two different networks? I'm not getting that question. Okay, Deepa is asking how the resource allocation is done for the internet integrated satellite and terrestrial network in 6G. Of course, Deepa, they will have some mechanism because we are using some different set of spectrums as well, and they have to have some kind of resource allocation application. So if you look at the open architecture, there is something called RIC. But even though if it is not the open architecture, there has to be somebody, some device who is doing making the decision on the the resource allocation part of it. Right. So I will be sharing the feedback and the assessment link with the team, and they will share it with you, and then you will be able to complete that feedback. Right. Feedback and assessment. Right. Uh, okay. Okay. So it says we can use LT and Wi-Fi. Okay. So Professor, if you see, it's not about. First of all, we need to understand that we are not talking about two different layers of two different network talking to each other, right? When you look at these kind of architecture, we typically call them as uh, you know uh, how to say this. We in LT we used to call it as a LAA and LWA. LAA is called as license assisted access. In that case, we are using two different spectrums as LT only. So we use LT on a licensed band and LT on a unlicensed band as well. LWA talks about bringing these two technologies together, LT and Wi-Fi, but there has to be some type of gateways in between. In case of 5G, we have a component called as N3IWF. N3IWF is called as non-3GPP interworking function. There are two more called as TNGF and WAGF, which can even communicate with the wireline network and untrusted or trusted Wi-Fi network, right? So whenever you want to talk about the devices who can speak different languages, you need to bring in the gateway nodes. Or you need to bring in some kind of translations in between. This is how it can work. Okay, Mr. Nagarajan says, how do AI and ML contribute to improve spectral efficiency in 5G and 6G network? How does AI differ from cloud-based AI in managing telecom? Edge AI differs from cloud-based AI in the managing telecom applications. Now, sorry. Now, first of all, improving spectral efficiency is one of the key area for the AI/ML in 5G. How it does that? That detailed discussion that can happen based on the optimizing the power, optimizing the resource allocation, optimizing the MIMO combinations or MIMO configurations. There are lot of things related to that. Now, can we discuss that all those things in such a short time? We cannot. Right? So there are the spectrum management or Spectral efficiency management is one of the key area for AI/ML. How does edge AI differs from the cloud-based AI in managing telecom application? So it is not about the AI application, it is about the location. Now, what does that mean? If you try to do something at the edge, it is able to give you a faster response. It is going to give you a faster response. And it can also work with some models which are called as federated learning, where the AI model is not running in the centralized location, it is running at the edge, and it can give you faster response, and it can also give the insights of this insight of this model to the global model as well, as we talked about in the federated learning part. Right. Mr. Abhijit says, please share the PPTs. Abhijit, sorry, I don't share the PPT of these sessions. Explain how ML models are trained to adapt to real-time changes in the traffic patterns. Mr. Nagarajan, so if you see, we already talked about it. There has to be some, first of all, we have to have some kind of data, some kind of test data. After having the test data, we have to train our model. And after training those models, we have to give them some kind of, first we have to give them train data, not the test data. We have to give them training data. Based on that, we are going to train the models. And after training those models will be able to adapt to the real-time changes in the network traffic patterns, and that we were testing with the test data. Right. Okay. Deepa says terrestrial communication using simulated. I'm not very well aware about it. Simulated test bed, how you're doing it. So there are hundreds of things, and I'm not really aware about it. What kind of simulation test bed you're using for both these things, integrated satellite and terrestrial communication. Right. So with this, I think we are very close to the end of the session. Over to you, Mr. Arvind. Thank you very much for giving this opportunity. This is my third and the last session. And thank you for giving this opportunity.
Yeah.
My pleasure to talk to all of you. Thanks a lot.
So, Sanjay ji, your lecture was really, I think, inspiring and informative. So thank you once again for your time and expertise. Thank you so much.
Yes,
have a good night.
Have a good. Take care. Bye. Thanks. Bye.
Okay, bye. Okay, participants, we will share the feedback link in the chat box soon. Okay, or I think you already receive in the WhatsApp group. So please use the link and fill the feedback. Okay.
I have already shared the feedback link in WhatsApp group.
Okay, sir. Okay.
Okay, so thank you very much, everyone.
Okay, participants, have a good night. Bye-bye.